welcome to 9.1. We're going to start talking about inference. We're going to be able to test a claim, and we're going to do that using significant tests. So we're going to have hypotheses and whatnot. So first thing we're going to do is we're going to talk about kissing the right way. And it's quote unquote the right way. Because what happened was the San Gabriel Valley Tribune said that most people are kissing the quote unquote right way. That is, according to a study, the majority of couples prefer to tilt their heads to the right when kissing. So in the study, a researcher observed a random sample of 124 kissing couples. They were observed tilting their heads to the right when they kissed. Out of 124 kissing couples, we have a proportion here. We had 83 were observed tilting their heads to the right. So we got a statistic here that P hat is equal to 83 over 124. Which is going to be approximately 0.669. I believe that's a rounded number, I'm not sure. So what we'd like to know is this evidence that couples tilt their heads to the right when they kiss? So I've set up a simulation that will help us determine whether a statistic as great as this could happen just by chance. Okay, so I'm going to go to my calculator, and I've actually set some stuff up ahead of time. So I want to do 20 simulations. So I have sim 1, sim 2, sim 3, sim 4, and so on. And first thing I'm going to do is I'm going to develop, I'm going to generate, rather, some random integers using my rand_int function. And I want those to be random integers 1 or 2. And I want 124 of them. And before I started this, I want to determine, hey, so this is going to represent 124 people, right? And if I just choose at random, whether they go to the right or to the left, I'll choose one as a right tilt, right? And 2s will be left tilts, right? So what I'm doing is I'm simulating this thing at random, where if there were no actual preference, right? If it were the case that people go right or left, and there is actually no preference, then what this simulation matches that particular scenario. So I'll hit enter, and there we go. So I have number 1 is a left tilt, number 2 is a right tilt, number 3 is a right tilt, number 4 is a right tilt, and so on. I'm going to go ahead and copy this in. To each of these. Oops, there's an extra equal sign there. We don't want that. Syntax. So we'll go ahead and do this lots and lots of times. Whoops. Oh. Not sure why it keeps telling me that I'm going to overwrite data. Let's go ahead and just write. I'm going to copy that instead. I think that'll help the problem. Okay. Okay, so I'm going to go equals, that's better, equals, not very exciting, but we're actually doing this kind of a fast way. Oops. What is going on here? Let's scroll over. And kiss tilt is going to be it's going to be my distribution of my simulation. All right, so now that we've got that, right, we've got 20 simulations. I've decided that a 1 is a right tilt. Now let's go ahead and count up how many there are. Now that could be really hard, except for that I've set up, there's a command that will actually count up the number of ones in sim1, and it's that. So I got 58, and then I can go up and change that to sim2. I can go up, that's interesting, and change that to sim3. Good. Go up and change that to sim4. And I'll go up again. We're going to count up the ones in sim 5. Not very exciting to watch, but it's a pretty cool process we're going through. Oops, I did sim 6 twice. We'll count that one. We'll go 7. 8. 9. 10. 11. 12. 13. 13, 14, 15, all right, and there they are. Okay, so now that I've got my numbers from my simulation, I'm going to go back over here and put those numbers into KISS tilts. So I had 58, 58, 62, 65, 71, 66, 68, 46, well that's a really low number, 60, 60, 66, 62, 66, 66, 60, 59, 61, 62, 66, and 52. Awesome, right? We did 20 different simulations, so that looks good. So let's go ahead and look at the distribution of our KISS tilt, is what we're calling it, right? So let's look at that. So let's go down to KISS tilt, and there it is. All right. And so what we're interested in is how many times we wound up getting a value that was over. What was our value that we found here? Our value was 83, right? How many times in our simulation did we get a value of 83? Never. So it seems highly unlikely then that that value of 83 people out of 124 tilting their head to the right when they kiss happened by chance. It's very, very unlikely that that happened just by chance, because we did the same thing using just chance, just using a random number generator, where each event has the same probability of occurring, and we never got a statistic that was as high as what we had here. So I feel like this is evidence that people that people actually tilt their heads to the right when they kiss. In other words, the result that they got from this observational study didn't just happen by chance. Okay. And we'll come back to this as we go through this particular section of the chapter. But for now, I would like to talk about a couple of ideas that are really, really important for us to do significance tests. So we're going to state hypotheses. Our hypotheses are going to be one of two. We're going to have both. We'll have the null hypothesis, which we're going to call H naught, or H sub 0. That's our null hypothesis. All right. What we're doing for this is we are trying to find evidence against this. Okay. All right, so we want to find evidence that the null hypothesis is not true. Our other hypothesis that we'll deal with is our alternative hypothesis. And the notation we'll use for that is H sub A, alternative hypothesis. Makes sense, right? And we are trying to find evidence that supports this hypothesis. Let's see. Okay. So let's go ahead and get to an example that will help us to determine what our null and our alternative hypotheses are in a particular situation. So in this case, there's this guy Mike. He wants to improve his play. His friends, like, your clubs are garbage. If you want to play better, you need new clubs. Hey, try my clubs. In particular, try my 7-iron. And we'll see if it's the clubs or if it's you. So Mike knows that his mean distance with the 7-iron is 175 yards, and that on average, his shots tend to be around 15 yards from his mean distance of 175 yards. So he's going to go ahead and check and see if this 7-iron makes his shots more consistent. Right? It's going to decrease the variability. So he's going to go to the driving range, hit 50 shots, and see what happens. So if his standard deviation changes, right? If his standard deviation gets lower, then that's going to be evidence that the new 7-iron actually helped with the variability of his shot. Okay? And perhaps that means that he needs new clubs, that he'll do better if he gets new clubs, if that's what he's trying to do. So then, it seems that if it doesn't work, what we're saying is, hey, well, if it doesn't work, then I think your standard deviation is just going to stay the same, right? Right? Now his friend would like that to not be true, right? He thinks that he knows what's wrong with his friend's golf shot. So he's going to say, hey, I think that what you need is new clubs. If he doesn't need new clubs and he tries this new 7-iron, then his standard deviation should be the same. His friend would like to find evidence to refute that claim. So his friend would really love it if his alternative hypothesis is true and his standard deviation becomes less than 15. So if he needs a new 7-iron, then it should be the case that the standard deviation is less than 15. So if we were going to do a hypothesis test on this, we would want to refute the claim that his standard deviation is 15 and find evidence to show that the standard deviation is actually less than 15. So in this case, we wanted to know if his standard deviation was less than 15, right? But what happens if he just wants to know if it's different, right? So I want to talk very briefly about different ways that we can write our hypotheses. All right, so we can have our hypotheses can be one-sided. All right. So a one-sided hypothesis is going to look like this. We're going to have H naught is going to be a parameter equals some value. And then our alternative hypothesis, H sub A, is going to be our parameter is going to be less than a value, or we could have our parameter greater than that value. So that's what a one-sided alternative hypothesis looks like, okay? However, there's another option. We could have a two-sided value, okay? So we could have a two-sided alternative hypothesis. And it's going to look like this. Our null hypothesis will be that we have some parameter equal to some to a value. And that's always the way that's going to be. And then our alternative hypothesis will be that the parameter is not equal to some value. All right, guys, so an example of why you would want to use something like this, right? What if you wanted to argue that the mean heart rate, mean resting heart rate of students in this class is 70 beats per minute? It's a little high. Then your alternative hypothesis would be that it is not 70 beats per minute, right? So that means that you would reject your null hypothesis if your heart rate was above 70 beats per minute or if it was below 70 beats per minute, right? If it was highly unlikely that the actual mean heart rate of students in this classroom was 70 beats per minute. Okay, so that's an example of how you would use that. And again, 70 is probably really high, but whatever. All right, moving right along. Now we've talked about that. I wanted to talk a little bit more about the kissing. I have right here a dot plot of a plot of the distribution of 500 trials of this simulation. So I did 20 trials, and in my 20 trials that I used that I did just with my calculator, and I think also the one we did in class, we got 0, right? 0 cases where we had 83 or more. In this case, it looks like there is one. There's only one, this one right here, right? And we calculate that as a 0.002 probability that you have 83 or more couples kissing, right? So the probability of something like that happening by chance is 0.002, right? Which is extremely unlikely. So then we would say that there's very convincing evidence that couples prefer to kiss the quote-unquote right way, with their heads tilted to the right. All right. So again, talking about kissing, really weird that this comes perfectly at this time of the year. And people are trying to kiss each other. Germs. Alright. So in this kissing example, can you guys see this alright? Do I need to enlarge this? Okay, we were estimating the probability we'd observe 83 or more couples tilting to the right when observing us. Yeah, right, we know this whole setup, okay? We know what V hat was. Alright. So in this case, what does it mean that what does this mean? So let's interpret all this stuff. Let's interpret this null hypothesis, okay? We're saying that we think that P, the actual proportion of people, is half, right? It would make sense that if this is not occurring, if there's no influence, right? Think about it. If there's actually not a preference, then over the course of many, many observations, you should see that people tilt one way or the other an even amount of times, right? So half of them tilt right, half of them tilt left, right? If there is indeed no preference, just like flipping a coin. A coin has no preference, right? It's a fair coin. After many, many, many observations, you should see that the proportion of heads should approach 0.5, right? Same thing here. So that's what we're saying. We're saying, hey, we would like to find evidence against the statement that the true proportion is 0.5. Right? And we actually believe that the true proportion is greater than 0.5, and we want to find evidence that supports that. In our simulation, we found out that our sample statistic, right, our sample proportion, turned out to occur very, very infrequently, right? Or we could say that the probability of occurring is very low. And because that probability is so low, we're going to say that it's unlikely for that result to occur if there actually is no preference, right? And that's the whole idea in a nutshell of what we're going to be doing for the rest of the class. This is really, honestly, what we're doing now for the rest of the year. All right, just using for different cases, different scenarios, different data sets. We'll be able to do it for bivariate data. Well, we're starting off by doing it for proportions. We're going to be able to do it for sample means. We're going to be able to do it when we're comparing two sample means. We're going to be able to do it when we're comparing comparing two distributions to see if indeed they are alike as they should be. That's what we'll use chi-square distribution for that. And then lastly, we're going to do this for least squares regression. And we're going to say, we're going to be able to make inferences using least squares regression. So that's the rest of the semester in a nutshell. And we're not doing ANOVA, nor will we do a Poisson distribution. So, so let's move on and talk about Mike again. I love how this lesson was really well built by whoever this was really well built, well written. because we're able to come back and refer to all these problems, which I like. So get a little deeper. All right, so we already determined what the null and alternative hypotheses were for this, right? So we actually found out that he went ahead and got a standard deviation of 13.9 yards after hitting his 50 shots, right? He performed a significant test and got a p-value of 0.2. So what does this mean? A p-value of 0.25. Let's talk about that real quick.
Wait.
All right. The p-value is the probability that our statistic will take on a value as or more extreme. As the value observed. And so in this case, this p-value is saying that there's a 0.25 probability. The probability that the standard deviation would be 13.9 yards is 0.25, right? So 25% of the time, we would expect for the standard deviation to be that extreme. All right, so I guess I already did this. Right. So let's do A now that I already did B. What does it mean for the null hypothesis to be true in this setting? Right? So, and another way that we say that is, if this is true, the language that we use is we would say, we fail to reject. Okay? So, if we find convincing evidence that the actual standard deviation after he hits 50 shots is 15, then what we're saying is that the null hypothesis is true. And we fail to reject the null hypothesis. I mean, do you think, so if it's the case that you take those 50 shots, you find that there's only a 25% chance that that you would get a value this extreme, would you say that that's convincing evidence that he needs new clubs? Would you say that it's convincing evidence that his actual standard deviation using the new clubs is different from, or less than rather, 15? I don't know. 0.25 is actually 1 out of 4 times. It's actually fairly likely. That's a fairly likely event, right? Those are decent odds. So I would say that there's really not convincing evidence at that point to support that that he needs new clubs, right? That when using the new clubs, his standard deviation was actually less than 15 yards. So I feel like what this the conversation that this really lends itself to this begs the question, right? How low does this probability need to be, right? How low? I mean, we said 0.25 is probably not low enough. So what's low enough? Right? What's a low enough probability? And what we call that our alpha level. I'm writing in cursive. The alpha level. So our alpha level tells us the level of statistical significance. All right. So we can decide on an alpha level ahead of time, and then after performing some sort of inference test, what our inference test will spit out is an alpha level. If our alpha level is above our predetermined alpha level, then we will fail to reject the null hypothesis. If our alpha level is below the alpha level that we predetermined, then we will go ahead and reject the null hypothesis, which means that we accept our alternative hypothesis. I'm going to say a lot of crazy long sentences that have a lot of logical links in them, right? Throughout the rest of the class, I'm going to say a lot of things like that. So imagine we had an alpha level of, I don't know why I want to write that in cursive. It's so strange. Imagine we wanted an alpha level of 0.05, which is extremely common. So our level of significance is 0.05. If we were to get an alpha level of I guess 0.13 or something like that. Let's make it obvious. Then we fail to reject and I'm not going to say the null hypothesis. I'm going to say we fail to reject H naught. In other words, right, if we got that alpha level, we would say there is not enough, it's not rare enough that this certain statistic would occur, that we would say that it happened just by chance. Or sorry, that it couldn't have happened just by chance. Sorry for that. But, so if this was our alpha level, if we wound up with an alpha or an alpha value of I'm sorry. I used the wrong terminology here. I apologize. It should be p-value. Sorry. So if our p-value and I said 0.17, something like that. Okay. But if we had a p-value equal to 0.03, then we reject the null hypothesis. And this is exactly the language that you want to use in your answer. And I don't want to say the null hypothesis, I want to say we reject each nut. And it means that so when we reject our null hypothesis, we are saying that there is significant evidence that the statistic that we arrived at, that we got from whatever we did, or rather the probability that that statistic would occur, is so low that we know that it didn't just happen by chance. So that's what we're saying when we're doing the hypothesis. All right, so let's go ahead and do another example. Hey, more kissing, yay. All right, so we estimated a p-value based on a simulation. Because this p-value was small, we're going to reject the hypothesis that p is 0.5. In other words, so we're going to reject the null hypothesis because we wound up with a p-value that was very small. So we're going to say we have convincing evidence that couples prefer to kiss the quote-unquote right way. But in our lesson 9 example, we wound up with an estimated value of an estimated p-value of 0.25, right? That's a very large p-value. So we fail to reject the null hypothesis. In other words, we don't have convincing evidence that Mike is more consistent when he uses the new lesson 9. So this is just really getting us into learning a lot of terminology, learning how to use it, learning what it means when we come up with a certain value for a p-value, level of significance. We're just laying down the groundwork, and then we're going to start doing some actual inference as we go. All right, we need to talk about what happens when we make mistakes, because there are errors, and we need to make sure that we don't make them, and they're actually so common that they've been named. But first, let's do another example so that we can get this. Yeah. We'll talk about type 1 and type 2 errors next.
Type 1, that's what happens if you do multiple t-tests.
Okay.
That's why you do multiple.
Okay, so you reject the null hypothesis when the null hypothesis is actually true, because you get an incorrect p-value. All right. No matter. Let's go ahead and do this, and then we'll talk about type 1 and type 2 errors. All right, Xenon. Wow. His parents didn't think that through. All right. You gotta really think that. Xenon. Do they like? He wants to know if kids like name brand potato chips, or if they prefer them over generic potato chips. He's randomly selected 50 students. Great. So he's got a simple random sample. And had each try both types of chips in random order. Overall, 32 of the 50, so we got a p-hat value of 0.64 students, preferred the name brand potato chips. He performed a significance test using the hypotheses. His null hypothesis was that the p-value was 0.5, right? Meaning that there's no preference, right? It's like flipping a coin. And the alternative hypothesis that indeed his proportion of the population is greater than 0.5, meaning that there is a preference, and that preference is towards name brand chips, right? Fantastic. He got a p-value of 0.239. So what conclusion will you make at each of the following significance levels? Not a very difficult example. At the 0.5 significance level, we would reject the null hypothesis, right? But at the 0.01 level, we would fail to reject. If we reject the null hypothesis, we would say that there is convincing evidence that the actual proportion is greater than 0.5, meaning that students prefer name brand potato chips. Or rather, we should say that there's convincing evidence that that's true. We can't make any sort of definitive claim like I just did, so I made a mistake. You can't say kids prefer potato chips. You have to say there's convincing evidence that the kids prefer name brand potato chips. So at least you got to see what a mistake looks like. You don't want to do that. You want to say there's evidence for that, right? And if we fail to reject H0, if we fail to reject our null hypothesis, then we would say that there is not convincing evidence that the actual p-value is not p-value, that the actual proportion is greater than 0.5, and thus we don't have convincing evidence that kids prefer name brand potato chips. Lots of talking, lots of words. We're going to do lots of writing as well. So our answer are going to have lots of like logical statements in sentences. It's just part of it. Okay. All right, so let's talk about a type 2 and a type 1 error, okay? And it's very easy to get these confused. There's a little hint here. Hopefully it works for us. A type 1 error. We use the Roman numeral 1 for that. Error happens when we reject our null hypothesis, when our null hypothesis is true. A type 2 error occurs when we fail to, and this is the hint, a little way to remember this, when we fail to reject our null hypothesis when our alternative hypothesis is true. Reject H not when H survey is true. What does it get? So we reject our null hypothesis when our null hypothesis is true, or for type 2, we fail to reject our null hypothesis when our alternative hypothesis is true.